silent forces decide the rhythm of modern life, flowing through walls, wires, and even the air, unseen but unstoppable. Every second, electricity keeps cities alive, wakes alarms, moves data across oceans, and keeps hearts beating inside hospital rooms. It looks simple. Flip a switch and light appears. Touch a screen and the world responds. But behind this everyday miracle hides a truth that still unsettles physics. Electricity is one of the most studied forces in history, yet at its deepest level, scientists still struggle to explain what it truly is. Not how to use it, not how to control it, but what it actually means in the fabric of reality. This video explores that gap. It starts with what electricity appears to be, then slowly peels away the layers that most textbooks skip. You will learn why electrons do not behave the way common explanations suggest, why energy moves faster than the particles carrying it, and why electric fields are treated as real physical objects, even though no one can touch them. Along the way, this story reveals how early experiments confused even the greatest minds, how equations predicted invisible waves before anyone could detect them, and how modern physics still relies on models that work perfectly without fully making sense. There are moments in science where answers only create deeper questions, and electricity is one of those rare cases where progress and mystery grow together. By the end of this video, you will understand why engineers can build global power grids while physicists still debate what actually flows through the wires, why electricity behaves both like a substance and like empty space, and why one of the most useful forces ever discovered remains one of the least understood at a fundamental level. Stay until the end, because the final insight changes how electricity is usually explained and shows why this puzzle matters far beyond light bulbs and batteries. It connects to the limits of human knowledge and the unfinished story of physics itself. Welcome to the channel, where simple explanations meet deep questions. If you enjoy uncovering hidden layers behind everyday realities, subscribe now and stay with us as we explore the forces that quietly shape the universe. Electricity begins with one simple idea that hides enormous complexity. Matter is made of tiny particles, and some of these particles carry charge. Electrons carry a negative charge. Protons carry a positive charge. This difference creates attraction and repulsion. Opposite charges pull toward each other. Similar charges push away. This push and pull is not visible, but it is real. It shapes how atoms form, how materials behave, and how energy moves. When charges stay in place, nothing dramatic seems to happen. But when charges begin to move together in an organized way, electricity appears. This movement is what we call electric current. In metals, electrons are loosely bound and can drift through the material. They do not race forward like cars on a highway. Their motion is slow and scattered, yet energy moves through the system almost instantly. This contrast between slow particles and fast effects is one of the first hints that electricity is not as simple as it seems. To make charges move, there must be a reason for them to move. This reason is voltage. Voltage is not a substance. It is not energy itself. It is a difference. It describes how strongly charges are pushed from one place to another. When there is a higher electric pressure at one point than another, charges feel a force. They respond by drifting along available paths. Wires provide these paths. The greater the voltage, the stronger the push, the greater the resistance, the harder it is for charges to move. From these ideas come the basic rules taught in schools. Current depends on voltage and resistance. Power depends on current and voltage together. These relationships work extremely well. They allow engineers to design circuits that power cities and devices that fit in a pocket. At this level, electricity feels understood. It behaves predictably. It follows clean formulas, but these formulas describe results, not reality itself. Behind these practical rules stands a deeper framework that reshaped physics in the 19th century. This framework is built from a small set of equations that describe electric and magnetic fields. These equations do not talk directly about electrons flowing through wires. Instead, they describe invisible fields that exist everywhere in space. An electric field surrounds any charged object. A magnetic field surrounds any moving charge. These fields can push on other charges, even across empty space. According to this view, electricity is not just about particles bumping into each other. It is about space itself being altered by charge and motion. When a charge moves, it changes the field around it. That change can travel outward, carrying energy with it. This idea was revolutionary because it removed the need for direct contact. Forces could act through space. These equations brought electricity and magnetism together into one unified picture. Before this, electric effects and magnetic effects were studied separately. The equations showed they are deeply connected. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. This feedback allows energy to move through space as waves. These waves do not require wires. They do not require matter. They can travel through a vacuum. Long before antennas existed, the equations predicted such waves. Later, experiments confirmed them. Radio waves, microwaves, infrared light, visible light, ultraviolet light, X-rays, and gamma rays are all the same phenomenon. They differ only in frequency. This result was one of the greatest successes in the history of science. It showed that light itself is an electromagnetic wave. Electricity was no longer just a tool. It became a window into the nature of reality. Despite this success, the picture created by these equations is hard to visualize. The equations describe fields that fill space, but what exactly is a field? It is not matter. It has no mass. It cannot be held, yet it carries energy and momentum. It can push charges and bend trajectories. It can exist even where no particles are present. In this framework, when a battery is connected to a wire, electrons begin to drift, but the energy that lights a bulb does not ride on those electrons alone. It flows through the electric and magnetic fields surrounding the wire. These fields extend into the space around the conductor. This means electricity is not confined to metal. It spreads into the environment. The wire merely guides it. This idea challenges the simple picture of electrons carrying energy like buckets of water. Inside a conductor, electrons do move, but their motion is chaotic. They constantly collide with atoms in the lattice. Their average forward speed is extremely slow. In many cases, it is measured in millimeters per second. Yet when a switch is flipped, the effect is felt almost instantly along the entire circuit. This happens because the electric field rearranges itself at near light speed. The field tells charges everywhere how to move. Energy flows through the field, not by waiting for individual electrons to travel long distances. This creates confusion because the visible actors, the electrons, do not behave in a way that matches the speed of the outcome. Some descriptions focus on electron flow, others focus on field propagation. Both are correct in limited ways. Neither fully captures the whole picture on its own. The difficulty increases when trying to explain where energy actually resides. In a simple circuit, energy leaves the battery and arrives at the load. But inside the wire, electrons mainly shuffle around locally. The energy is stored and transported in the surrounding fields. This means the space around the wire is active. It is not empty. It plays a central role. This idea feels unnatural because everyday experience does not prepare the mind to treat empty space as a carrier of energy. Yet experiments confirm this again and again. Remove the fields and nothing works. The fields are not mathematical tricks. They are physical entities, even if their substance remains unclear. This leads to deeper questions. Are electrons the main players in electricity, or are they supporting actors responding to fields? If electricity is about fields, then what creates the fields in the first place? Charges create fields, but charges themselves are defined by how they interact with fields. This circular definition works mathematically, but it leaves a sense of incompleteness. At no point does the explanation settle into a simple physical picture. Each layer explains behavior while raising new questions about meaning. Disagreements appear even in something as common as current flow. In some explanations, current is described as electrons drifting through a wire. In others, it is described as the movement of energy through fields. In alternating current, electrons barely move back and forth around fixed positions, yet energy travels across entire power grids. In this case, describing electricity as particle flow feels misleading. The electrons mostly oscillate. They do not journey from power plant to home. Still, the light turns on. This suggests that electricity is less about transport of matter and more about coordinated motion guided by fields. Another strange aspect appears when considering resistance. Resistance is often explained as collisions between electrons and atoms. These collisions slow electrons down and convert electrical energy into heat. This picture works well at a basic level, but it does not explain why resistance depends on temperature in specific ways, or why some materials suddenly lose all resistance under certain conditions. Superconductors allow current to flow without energy loss, yet electrons still interact with atoms. The field-based view handles this better, but it still relies on abstract concepts that resist intuitive understanding. As theories improved, the classical picture was joined by a quantum one. In this view, electrons are not tiny balls moving along clear paths. They are described by probability waves. Their positions and velocities cannot be known exactly at the same time. In a conductor, electrons fill energy levels and respond collectively to fields. Current becomes a property of the whole system, not individual particles. This explains many effects that classical theory cannot, yet it makes electricity even harder to picture. The electron is treated as a point with no size, yet it has charge and mass. Its electric field extends infinitely far, but its location is uncertain. This combination defies common sense. The field itself becomes quantized in this deeper theory. The electromagnetic field is made of excitations called photons. These photons carry energy and momentum. Light is a stream of photons. Radio waves are streams of photons. Even static electric forces can be described through exchanges of virtual photons. This picture unifies electricity with other forces, but it also pushes understanding further away from everyday language. At this level, asking what electricity is becomes a question about the structure of space, time, and interaction itself. Even with these advanced models, practical explanations still rely on simplified stories. Textbooks choose the version that best fits the situation. Sometimes electrons are the focus. Sometimes fields take center stage. Sometimes waves are emphasized. Each approach works within limits. None tells the full story alone. This patchwork is not a failure. It is a sign that electricity operates across multiple layers of reality. It connects the motion of particles, the behavior of fields, and the geometry of space. The strange part is that all of this complexity hides behind ordinary experiences. A phone charging on a desk triggers quantum field interactions, guided by equations written centuries ago, moving energy through space faster than any particle involved. The same force that binds atoms also powers global communication networks. Yet when pressed for a single clear definition, physics offers descriptions, models, and equations, but no final image. Electricity remains both familiar and elusive. It is something that can be calculated with extreme precision and still not fully pictured in the mind. This tension sits at the heart of the subject, quietly reminding us that understanding behavior is not the same as understanding essence. As physics pushed deeper into the nature of electricity, a quiet conflict began to emerge between two ways of describing reality. One way focuses on matter. This view says electricity comes from electrons, tiny charged particles moving through materials. The other way focuses on fields. This view says electricity comes from invisible structures that fill space and tell charges how to move. Both views work. Both are supported by experiments, yet they do not sit comfortably together. When physicists describe electricity as electrons flowing, the explanation feels concrete and mechanical. When they describe it as fields shaping space, the explanation becomes abstract and geometric. The strange part is that the field is not just a helpful idea, it behaves like a real physical thing. It stores energy. It carries momentum. It can exist even where no particles are present. Empty space becomes active. This challenges the instinct that reality is made only of objects. In electrical systems, the space around the wires is just as important as the wires themselves. Energy often travels outside the conductor, guided by the shape of the field. This forces physics to treat space not as a passive background, but as an active participant. Trying to picture an electric field creates immediate problems. It has no surface, no texture, and no clear boundary. Lines drawn in diagrams are only symbols. The real field exists everywhere at once, changing smoothly from point to point. It responds instantly to changes elsewhere, limited only by the speed of light. When a charge moves, the field around it adjusts. That adjustment carries information. In this sense, electricity is less like a substance and more like a conversation between charges and space. Yet space itself is invisible. This makes the explanation feel incomplete, even though the math works perfectly. The confusion deepens when attention turns to the electron itself. The electron is often treated as the smallest unit of electric charge. It is described as a particle, yet it does not behave like a tiny solid object. In quantum physics, the electron has no known size. It has no internal structure. It is treated as a point, an object with position but no volume. At the same time, its electric field extends infinitely outward. This creates a strange picture. A point with no size somehow influences the entire universe. Attempts to assign a physical shape or boundary to the electron fail. Experiments show no evidence of internal parts. The electron appears fundamental. This raises questions that physics cannot yet answer. How can something with no size have properties like charge and mass? What exactly is carrying the electric field? Where is the energy stored when the electron is at rest? Quantum theory describes the electron using probabilities rather than paths. The electron does not follow a clear trajectory. Instead, it exists as a spread-out wave of possibility. Only when measured does it appear at a specific location. This makes the idea of electrons flowing through a wire misleading at a deep level. What flows is not a stream of particles in the usual sense, but a coordinated shift in probability patterns across many electrons at once. Current becomes a collective effect, not a simple motion. This explanation matches experiments, but it abandons everyday intuition. Electricity becomes a statistical phenomenon rooted in uncertainty. The electric field itself also becomes strange under quantum rules. It is no longer smooth and continuous. It is made of discrete excitations. These excitations behave like particles of light. Even static electric forces can be described as exchanges of fleeting entities that cannot be directly observed. This means that what feels like a steady push between charges is actually the result of countless microscopic interactions. The calm surface hides violent activity beneath. The field vibrates even in empty space. This restless background energy never fully disappears. Electricity becomes tied to the deepest structure of the vacuum. The challenge is that classical and quantum descriptions do not fully align. Maxwell's equations describe fields as continuous and smooth. Quantum theory describes them as quantized and probabilistic. In many situations, the difference does not matter. The classical equations work so well that engineers use them daily without concern. Power grids, radios, and computers all rely on them. But when physicists try to merge the classical picture with quantum rules at every scale, cracks appear. Calculations can produce infinite values that must be carefully removed through mathematical tricks. These tricks work, but they feel artificial. They suggest that something deeper is missing. This mismatch shows up clearly when extreme conditions are considered. At very small scales or very high energies, classical equations fail. Quantum field theory steps in, but it relies on assumptions that are difficult to justify physically. The field is treated as fundamental, yet it arises from equations rather than clear physical principles. Some properties are simply inserted because they match experiments. This approach is effective but unsatisfying. It explains how electricity behaves without explaining why it must behave that way. Electricity also contains unresolved puzzles that appear even within classical physics. Certain setups produce results that seem to contradict simple interpretations of the laws. Induction effects can depend on the motion of observers. Energy transfer can appear to happen without a clear path. In some cases, changing a magnetic field produces electric effects that do not fit neatly into cause and effect sequences. These situations do not break the equations, but they challenge intuitive explanations. They force physicists to rethink what is meant by force, motion, and interaction. Some researchers argue that the standard picture hides deeper assumptions that should be questioned. One assumption is that fields are fundamental. Another is that space and time are fixed backgrounds. If these assumptions change, electricity might look very different. Alternative theories explore whether fields emerge from more basic structures, or whether charge itself is a manifestation of geometry. These ideas remain speculative, but they highlight how open the subject still is. Electricity may not be a single thing. It may be a surface expression of something deeper. The importance of these questions goes far beyond curiosity. Electricity sits at the center of modern physics. It is woven into theories of atoms, light, chemistry, and technology. It connects directly to the structure of matter and the flow of energy. Any attempt to unify physics must deal with electricity at its core. The same effort that seeks to merge quantum mechanics with gravity must also account for electric and magnetic forces in a consistent way. A deeper understanding of electricity could reveal new principles about space, time, and interaction. Technology continues to advance using models that work, even if their meaning remains unclear. Devices grow smaller, systems grow faster, yet the foundation remains partially mysterious. This is not a weakness of science. It is a reminder that understanding grows in layers. Electricity is mastered in practice, while remaining elusive in essence. The equations predict outcomes with stunning accuracy, but the story behind them is still being written. Each attempt to clarify the nature of electricity reveals new depth. What began as sparks and shocks has become a window into the limits of human explanation, where matter and space blur, particles lose shape, and fields gain substance. Electricity obeys our commands with incredible precision. It lights rooms, carries voices across the planet, and runs machines that shape modern life. Engineers can predict its behavior down to the smallest detail. Equations tell us exactly how it will move, how much power it will deliver, and how it will respond in almost any situation. In that sense, electricity feels completely understood. Yet beneath this control lies a deeper uncertainty that has never been fully resolved. Physics can describe what electricity does, but it still struggles to say what electricity truly is. Is it particles drifting through matter, or fields stretching through space? Is it a property of objects, or a feature of the vacuum itself? Each explanation works in practice, yet none feels final. This gap between behavior and meaning is what makes electricity so fascinating. It shows that even the most familiar forces can hide profound mysteries. The same equations that power our world also point toward unanswered questions about the nature of reality. Electricity sits at the boundary between the known and the unknown, between precise prediction and incomplete understanding. That is why, after centuries of study, one of the simplest and most useful forces still baffles physics today. If this exploration changed the way you think about electricity, support the channel by liking the video, share it with others who enjoy deep ideas, explained simply, and subscribe to stay with us as we continue uncovering the hidden questions behind everyday forces.